Again. So I'm still Ivo, and I'm now going to talk about zero overhead parallel scans for multi-core CPUs. This is based on a paper that we presented earlier this year at PMM. So yeah, the work is about scans on CPUs, and we've heard scan already a few times today, so that should help. But just to make sure everyone is on the same page, a scan computes the prefix sum or cumulative sum, which means that for each element it computes the combined value of our prior elements. So very simple example, if you have an array of 10, 11, 12, and 13, then the scan could be that the first element is 0 because there are no prior elements, and the next is 10, 21, 33, and 46. And there are various variants of the scan, because now I didn't include the value at the same index, but you could include that. You could have a right to left scan. So there are various variants of that. So you can execute this in parallel if the operator is associative. It's similar to parallel reductions. And yeah, you see scans in many parallel algorithms, including algorithms to filter or compact data, or as we've also seen, to partition data. It's used to flatten nested data, for sparse matrix multiplication, also in computer graphics, and in the break I quickly added parsing as another example, because that's also an example of scans. So just to make sure everyone sees one example of that, I have this example to filter data, but it's somewhat similar to partitioning that we've already seen today. So I'll quickly go over it. To say that we need to filter this array and only preserve all the even elements of this array, then we can first map over this to compute this whether an element is even. Then we get this array. Then I can perform a scan over that, and then for each even element, I now know where that element should go. For instance, element 36 has value 2, which means that it should go to index 2, because there are 2 elements before that that are also even. And I can do that with a scatter or a permute, and then I get the desired output. Then, yeah, we're talking about performance. We're talking about parallel scans. And yeah, it is possible to execute scans in parallel. And parallel scans are also faster than sequential scans if you have multiple threads. And yeah, you may have a machine that has like thousands of threads, and then you might not worry about this. But if you have a more real machine, then you might not know in advance if you have multiple threads available for this parallel scan. And if you take existing parallel scan algorithms and execute them on a single thread, then they're asymptotically as fast as a sequential scan, but they have a constant factor overhead over a sequential scan. I think it was around 50 to 70% performance over a sequential scan. And yeah, so the main question is, do we have multiple threads available? And you might not know that in advance, because the processor may also be executing other tasks. So for instance, it could be that we have 4 threads which are all executing some task, and then at some point thread B needs to start a scan. Well, in this case it's clear that we can execute a parallel scan because thread 3 is also available. So we can let them execute the scan together, and then will be faster than a sequential scan. But what now if the situation looks like this, where thread B wants to start a parallel scan, but it's the only available thread? At this point, we don't know if it's worth to start a parallel scan, because it could be that in the near future, task C and D both finish, and then we have 3 threads available to work on this scan, and then we're probably faster by doing a parallel scan. But it could also be that task C doesn't finish soon, and it could be that task D does finish, but that we then need to execute a different task. So it's difficult to predict if a parallel scan would be worth it. And we introduce those zero overhead parallel scans. First, if you compare this to parallel map or parallel reduction or fold, they already have practically zero overhead. If you take a parallel map or a parallel fold and execute that on a single thread, then it will be about as fast as a sequential map or reduction. And we can just start to execute them in parallel without knowing whether multiple threads will be available. And that's not the case for existing scan algorithms. Hence, we introduce parallel scan algorithms with no single-threaded overhead, or practically no single-threaded overhead, that are robust in changes to the number of threads. They allow more threads to assist in the scan after its start. So some terminology. An aggregate of a block is the combined value of all the elements of that block, and a block is a part of the array. A prefix is the combined value of all prior elements, and the goal of the scan is to compute all prefixes. And we assume left to right scans for simplicity, but it also applies to right to left scans. So we introduced various algorithms. The first one is based on reduced and scan, which is a classical three-phase scan algorithm. And so as a scan, we get some input, and we should compute the output. And I visualize them both here on this slide. And what reduced and scan does in phase one, it reduces all the blocks to an aggregate. So the total sum of all the elements in the first block gets a certain value, and we do that per block. And the colors in this visualization denote the different threads that are working. And those different threads will gradually work through this array until they have computed all the aggregates of the blocks of the array. Then we have a series of aggregates, and we perform a scan over these aggregates. And we typically do that sequential because we just have a few blocks, so it doesn't make sense to do that in parallel, depending on your setup. And then we now know the prefix values of all blocks, and then we perform a scan per block, starting at that computed prefix value. And again, this happens by all the threads. So that's how a reduced and scan works. And let's now introduce our assisted reduced and scan. Our assisted reduced and scan is essentially a sequential scan assisted by a parallel reduced and scan. During phase one thread works from the left of the array, and that thread executes a sequential scan. All the threads work from the right, and they perform the first phase of a parallel scan. So they perform the reduce phase. In this case, the orange thread is working in the sequential mode and starts from the left and directly computes the output for its part of the workload. And all the threads work from the right, and they perform a reduction until they meet somewhere in the middle. Now at this point, the output for the first three blocks is already ready. And we only need to do some more work for the last 5 blocks. So we need to perform phase 2 only on those 5 blocks. And more importantly, we only need to do phase 3 on those 5 blocks. And the thread that worked in a sequential mode can again help in phase 3. So as you see here, we did fewer work in this example. In an extreme scenario where there's only one thread available, all work would be handled in the sequential mode in phase 1, and we would have practically zero overhead. So to evaluate this, we did some benchmarks. This is a benchmark to perform a scan on a large array, and the yellow line is the standard reduced and scan, and the orange line with the open boxes is assisted reduced and scan, so our algorithm. And you can see that on one thread, it has a speed of exactly 1, meaning that it's exactly as fast as a sequential scan. And if you have more threads, then it's still slightly faster because we did a small part of the work in a sequential mode in phase 1, and thus have less work to do in phase 3. I was aware that 1TBB also has a somewhat similar optimization for single-threaded performance, but that optimization only works for single thread performance, because on more threads that doesn't give a significant benefit. However, this is not the fastest scan algorithm. That's the chain scan, as you can see here. And let's now take a look at how chain scans work. So chain scans are the state-of-the-art algorithm for scans on GPUs. And in this work, we show that it's also suitable for multi-core CPUs. So in the chain scan, we again distribute the array in blocks and let all the threads claim blocks. And after claiming a block, a thread will reduce that block to a single value, to an aggregate. And after it has computed that aggregate, it will share the aggregate. And then it will wait on the aggregate of the previous blocks to become available. So thread 1 can, after it has reduced the value, perform a scan over that because there are no prior blocks. But thread 2 needs to wait on the aggregate of thread 1 before it can perform its scan. And when it has that value, then it performs a scan. Then thread 3 also needs to wait on the aggregate of both thread 1 and thread 2. And then it knows its prefix, and then it can execute a scan. So you see that there is some synchronization overhead here. But this continues. So after the first 3 blocks are ready, threads will claim more work and continue this same process of sharing an aggregate, waiting on the prefix to become available, and then performing a scan. Then there is some synchronization cost. The chain scan with decoupled loopback reduces this the impact, and see the paper that introduced that, or our paper, for more information about that. But yeah, as I said, this is the state-of-the-art scan algorithm for GPUs. And on the GPU, this works well because we can store a block of the array in registers. Each block of the array is handled by a thread block. And in a thread block, we have many threads, and each thread has its own registers. So we can store all the values of a block in registers. And we can thus remember all the values between the reduce and the scan phase, and thus read each element only once. And typically, memory bandwidth is the limiting factor for a scan, so this is really beneficial. However, on a CPU, we cannot just store them in registers, because each thread has only a few registers, and then we would have a very small block. But instead, we can store them in level 1 cache by choosing the block size to fit in L1. And then all the values are stored in the cache between the reduce and the scan phase, and we only read them from main memory once. And then we get the same benefit. So that's how we adapt chain scans to CPUs. Let's now make them zero overhead. So we call those scans adaptive chain scans. They start in a sequential mode, and as soon as another thread assists in this scan, then they adapt to parallel mode. When a thread has claimed a block, then it will check if the prefix for that block is already available. If that's the case, then it performs it as a sequential scan. And if that's not the case, then it will perform the usual reduce and scan stages of the chain scan. So let's see that in action with some examples. So it could be that we start with only one thread available, and then we handle the first block in a sequential mode, we handle the second block in a sequential mode, and then another thread also becomes available and joins this computation. So what that thread does, it claims block 3, and then it sees that the prefix of block 2 is not available, so thread 2 will work in the parallel mode, and thread 1 will later then claim block 4, and that will then also switch to a parallel mode. In an extreme scenario, it could be that we are always stuck in the sequential mode, and then we have practically no overhead, because the entire scan is handled as a sequential scan. And it could also be that we directly start with many threads available, and then the entire scan, except for the first block, is handled in this parallel mode. Then, to go back to this benchmark, we see that indeed on one thread we have no overhead. We're as fast as the sequential scan because the open circles are our adaptive chain scan, and the red closed circles are the standard chain scan. So on one thread, we have no overhead, and on many threads, the adaptive chain scan is equally as fast as the chain scan. And the reason for that is that we only optimized for the sequential mode, which doesn't do anything if you have multiple threads available from the start. In the paper, we also have an analysis of the memory bandwidth to show that those scans are really close to the memory bandwidth that's available on the processor. So to conclude, we introduced assistive reduce and scan, and in the paper we also introduced assisted scan then propagate, which is another classic three-phase scan algorithm. Those are based on reduce the scan and scan then propagate, and in phase one thread performs a sequential scan, and it's assisted by all the threads performing phase one of a parallel scan. And then in phase 2 and phase 3, we have less work to do. It has 0 single-threaded overhead and slightly better multi-threaded performance. And then the adaptive chain scan is based on the chain scan with decoupled loopback, the state-of-the-art algorithm for GPUs. It reduces memory pressure at the cost of more synchronization. It starts in the sequential mode and adapts to a parallel mode, which gives it 0 single-threaded overhead. And it's faster than the classic three-phase scan algorithms, also on CPUs. Well, read the paper if you want to see the pseudocode for the algorithms, see benchmarks for compaction or filter. If you want to see the memory bandwidth analysis, we also have an analysis of the ratio between the sequential mode and parallel mode for the three-phase scans. And we explain the decoupled loopback of chain scans there. And you can also have a look at the papers that introduce reduced and scan and the chain scan. And that's all I had to say.
Questions?
I'm curious whether this the assisted technique might generalize to GPUs at all when you have one lane versus like a block of threads to work with.
That's an interesting question. So on a GPU, you're obviously in a different setting because you have many more thread blocks. It could still be useful to do something similar to this. Because in general, if you're executing a scan on the GPU, you can assume that you have enough things available. But what if you're executing a scan over a matrix and you want to perform the scan per row of the matrix? Then it could be that you could just assign one row to each thread block, but you could also do something with assisted reduced and scan, where you, in the beginning, just assign one row per thread block, but have the option that multiple thread blocks cooperate on one row. And then I think the assisted reduced and scan could help in certain configurations.
I had a question about the SIMD features of the CPU. Are these benchmarks leveraging the SIMD features on the CPU when you're analyzing the memory bandwidth?
I think I have compiled it for native, so then it should use all the SIMD instructions that are available.
Okay, because do you know how that has changed over time? Because I think we did some benchmarking a while back, and it seemed like once you started leveraging SIMD properly, without threading, you immediately saturated the memory bandwidth of the CPUs, and threading didn't actually gain you anything.
That's somewhat true. Like, you don't see a lot of scaling because you quickly hit the memory bandwidth of the processor. So yeah, here you see that the three-phase scan scales to 2, and the reduced or the chain scan scales to about 3 times. So you don't see a lot of scaling because you quickly hit the memory bandwidth. But there is still some scaling possible. So this is on an Intel processor. We also have an AMD processor at work, and there it's scaled less. It's a bit older processor. But yeah, that really depends on the processor in the end.
The scans are implemented with SIMD operator. Like, I assume it's a prefix sum that you're benchmarking.
Yeah.
So those are implemented using the SIMD scan operations.
So I did turn like as architecture native, so the compiler should be allowed to emit any factor instructions that are possible. I didn't inspect the assembly to see what it's actually doing, but I would expect that it's doing factorization over this. But yeah, if you compare this, for instance, to, I didn't do a lot of experiments on that, but on my laptop, Apple laptop has a lot more memory bandwidth with Apple Silicon chips. So you do see a lot more scaling there than you see on this x86-64 processor.
Thank you for the presentations, very nice, both. I have more of a philosophical question. So it's nice that your mechanism is able to combine sequential scan with various forms of parallel scans and such. But what if, like some sort of, you can optimize much better sometimes the sequential code than the parallel code, because, for example, you can fuse more aggressively, right, into folds and such. So this holds for one version of the code, but how would you, so this is philosophical in the sense that give us your thoughts on how do you go about if you have multiple versions of code, like one code in which only this is parallel and the rest is sequential, and another code in which you have two levels of parallelism that can be, you switch back and forth between?
Yeah, interesting open question. So first thing that comes to mind is, because we've also been talking about fusion in the office, and it seems like that with a chain scan, you can also fuse more than with a three-phase scans, because three-phase scans need to be implemented in different kernels or different loops, and the chain scan is executed as a single loop or kernel. Yeah, so you can fuse a lot more if you have a chain scan. So that's part of your question. In general, it also felt to me like that there might be more algorithms where a setup where you both have a sequential and parallel implementation could work. Though the difficult thing is, which you also saw in the chain scan, is that during the execution of some sequential work, it should be allowed that at any point a parallel thread starts the computation. And you could perhaps that's also a good option, make your life a bit easier by saying that if, in this case, thread 2 starts working while thread 1 is still busy with some block, that thread 2 should then wait until that block is finished, so that you add some more synchronization. But yeah, that also costs something. Yeah, difficult to say in general. I would hope that this idea of having both sequential and parallel variant could be helpful for more algorithms. Yeah.
So how do you compute the sequential scan? Is that just a loop where you add something to the previous element, or?
The sequential scan is just a regular loop with one accumulating variable.
Do you know how, because I've imagined that it's very tough for a compiler to factorize that due to the loop dependency. There are any like parallel algorithms used for that?
So I would expect that the compiler would just be able to detect this, because this is a standard scan. I don't know the names of all the, I think the Koch-Stone scan, can anyone confirm that? Is the scan that's used for SIMD level parallel scans. So that's, for instance, what's also used on a GPU within a warp and on a CPU in SIMD level. So that's a different scan algorithm than what you see here, but that's very well suited for this vector, for those vector instructions.
All right, let's thank the speaker again. Let's carry on discussing, but there's coffee that would